Now we're going to see the second of two video DVDs on quantum mechanics. This one is going to much more closely relate to what we focused on in class. Also, kind of the chronology of what we do. The graphics might help you appreciate a little more some of the references we made to standing waves, that type of thing. But I want to start off just by introducing what they start off. The evidence that we focused on in the book, and it's usually what it's focused on, as evidence for quantized energy states, as you know, was the bright line spectra of energized gases. So, for example, the four bright lines of hydrogen suggest that the electrons are arranged in certain quantized energies or allowed energy states, stationary states. There's another way of gathering evidence for that. And rather than energizing a gas and then looking at the light produced by those excited electrons as they refer to their lower allowed energy states, we can also use ionization energy data. We haven't talked about ionization energy yet. We will in section 650. But ionization is kind of what it sounds like. You take neutral atoms and then you bombard them with electrons of specific energies. And you carefully observe how much energy it takes to remove the electrons one at a time. The example that the video was proved is energizing calcium. So if you pass vaporized calcium through a beam of bombarding electrons and measure how much energy those electrons need to strip off calcium's electrons, you can get further evidence about energy states. So calcium, if we wrote the electron configuration of calcium this way, we don't normally separate them that way, but in terms of the evidence we're going to discuss, I'm doing it here. So 1s2, and then the second energy level, 2s2, 3.6. The 2 tells us that these electrons spend more of their time further from these. And then the new energy level, those spend more of their time further away from these, and these two spend most of their time further still. If we're going to remove successive electrons, and there's 20 of them, if we remove all 20, we expect that every time we take one electron away, it's going to take more energy to take the next one, because every time we take one electron away, what we're left with has an increase in positive charge. We expect it. What we might expect is that the ionization energies increase like that, but they don't. They increase discontinuously. So when we measure the energies, that's ionization energies, the first two come off pretty easy, and the second one takes more energy than the first, because as soon as we take one electron away, then we have a 1+ cation. You don't have to draw this, you'll see it in the video. But after the second electron is removed, the energy to take the third one away isn't here, it's way up here. So as soon as we take these two away and empty that energy level, that cloud, the next one we take away takes more energy.
Good morning. Sorry for the interruption again. Just 2 extra announcements. First of all, for the grade 12s who have signed up for their LinkedIn photo, please do show up. The media team has set up and they are ready and waiting for you. The second announcement is for the Vancouver Sunrun STM Nights team. Today is the last day to register if you were wanting to be a part of the STM team. Thank you.
The first two we take away take the least amount of energy. Second takes more than the first, we expect that. But it's way harder to take the third away than it was to take the second. Because after we take 2, now we're into a cloud closer to the nucleus. So when we take these 8 away, we're moving these. But after the 10th, it takes a lot more energy to take the 11th away, because now we're moving to a cloud closer to the nucleus. So that's the second energy. And after the 18th, it takes a lot amount of energy to get the 19th away, because now we're into the first energy level. So the fact that we get these discontinuous jumps in the amount of energy required is another way of gathering evidence about these layered energy states. And because we haven't talked about ionization energy yet, If you saw that on the video for the first time, it might not make sense. That's why I thought I'd introduce it. This isn't gonna take the whole period. And there's a couple of things I want to discuss after the video is over. You don't really have to take notes on it because it, except for that, it matches what we did in the book, virtually identical. Okay. This remote is. Get the lights in a second. Let's try that.
Defining structure. It uses the tool of atomic theory to promote the understanding of any pure material in terms of single units or building blocks. The units may be individual atoms or a group of atoms called a molecule. Pure solids or crystals are a three-dimensional network of a basic unit. Pure gas consists of freely moving molecules. Understanding how atoms behave toward one another is the key to chemistry. The reactants and products of chemical reactions are made up of atoms. Their behavior, how they interact with other atoms, depends on their outer surface.
Hydrogen gas and chlorine gas will give us some ultraviolet light, and then it turns into hydrogen fluoride.
This outer layer of atoms, and in fact their entire volume, is made up of electrons. So understanding electron organization leads on to understanding chemical substances and chemical reactions. This program looks at experiments that enable scientists to construct a model of electron arrangement in atoms. The 19th century model treated electrons as particles which were commonly represented as spheres. This classical model changed to the quantum mechanical model, where atomic orbitals or electron clouds represent those regions in space where electrons with a specific energy are most likely to be found. Its identity is determined by the number of protons in its nucleus, its atomic number. This atom with 20 protons, 20 electrons, and 20 neutrons is calcium. Chemically speaking, the electrons are really the only fundamental particles that count. How are the 20 electrons arranged around the nucleus? Do they orbit the nucleus like planets around the sun? Is there a way to find out about the forces holding them in place? In the 19th century, cathode ray discharge tubes revealed a great deal about the structure of atoms. Using similar apparatus, a beam of electrons generated by high voltages between the electrodes of a valve can be used to bombard gas atoms. When the beam is given enough energy, the accelerated electrons can strip the outer electron from atoms of the gas inside the valve. This process is called ionization, because a charged atom called an ion is produced. The energy needed to remove one electron is called the first ionization energy. It's possible to continue to remove electrons from ions by increasing the energy of the bombarding electron beam. The positive charge of the protons in the nucleus is always the same. We can plot the successive ionization energies for the calcium atom. Carefully describing the results can tell us about electron organization. First thing to notice is that the energy needed to remove another electron always increases. When an electron is removed, the attraction between the remaining electrons and the nucleus becomes stronger. Secondly, the way the ionization energy increases isn't regular. Removal of the third electron requires much more energy than the second. Removal of the 11th electron much more than the 10th, and the 19th much more than the 18th. The pattern of these jumps suggests that the 20 electrons are organized in groups. The ionization energies of electrons resemble the potential energies of books in a bookcase. 2 electrons in the outer or fourth energy level are easiest to remove, suggesting they spend most of their time on the outside of the atom. The next 8 electrons spend more time closer in, the next 8 even closer, with the last 2 electrons held most strongly in the first energy level. Experiment provides good evidence for the idea that electrons in atoms can be grouped according to their energy. It doesn't tell us anything about the form electrons take inside atoms. This experiment is really a set of careful observations of light, particularly light from various sources. It is a completely different way of studying electrons in atoms, yet it provides more evidence for an atomic model where the energy levels are layered.
So this would be the emission spectrum. So what we talked about.
In white light or sunlight is passed through a prism, we see a spectrum of colours. Bands of colour in a rainbow merge into one another through a continuous spectrum. The prism separates light according to wavelength or energy. Blue light has a shorter wavelength and more energy than red light. White light is composed of an even distribution of wavelengths. This spectroscope is an optical prism fitted with an eyepiece. If we look at white light through this instrument, we see a continuous spectrum of colours. If crystals of sodium chloride or common table salt are heated in a Bunsen flame, we see intense yellow light. Different metal salts produce different colours. This crimson flame is caused by strontium chloride. Here, the same salts in solution are mixed with the fuel of a broad flame. This is strontium chloride. And now sodium chloride solution. What would we see if we looked at the light from the coloured flames through a spectroscope? Sharp-edged coloured lines against a black background. Quite a remarkable observation. How does the light coming from a flame containing metal ions differ so dramatically from white light? What happens to the metal ions in the flame that produces separate lines of colour? A theory which explains this observation uses a layered energy level model of atoms and goes like this. Metal atoms in the gas phase absorb energy from the wide range or spectrum of energies provided by the flame, and their electrons become excited.
When they give it back,
This is a brief condition for the gas phase atoms, which are being carried continuously through the flame.
the only problem with that is it says 2 down to 1 is red. It isn't.
As the atoms cool down, the excited electrons return to the ground state, emitting their energy in the form of
We
coloured
can't
light.
see anything.
Coloured
2 down to 1.
because only exact wavelengths corresponding to the differences between energy levels are emitted.
I'm getting ready to say.
If this theory holds, then all atoms should exhibit an emission line spectrum when energized, and they do. Here are the visible emission spectra or line spectra for 3 elements. Every element's line spectrum is unique. Hydrogen is the simplest atom of all. It is 1 electron and 1 proton. At room temperature, it exists as diatomic molecules, which make up a gas that is lighter than air. And explosive. Energizing hydrogen could be dangerous, but we can safely observe the light from excited hydrogen atoms by using a high voltage discharge lamp containing a very small amount of gas. The light we see is purple, and analysed through a spectroscope prism, the visible emission spectrum of hydrogen is clearly made up of exact wavelength lines of red, blue, and violet colours. By detecting any invisible wavelengths coming from the lamp with electronic instruments, groups of lines in the infrared and ultraviolet regions of the electromagnetic spectrum can be found. These groups of spectral lines are named after the people who first observed them, as are the corresponding series of transitions to particular energy levels in the model of the hydrogen atom. Model needs many layers to account for the many lines in the emission spectrum. Historically, it was the relationship between the lines that interested scientists. In 1888, a Swiss schoolteacher named Balmer simply measured the distances between each line in the visible spectrum of hydrogen with a ruler. Using his knowledge of mathematics, he was able to fit the distances to an equation. Johannes Rydberg went further by showing that all the lines in the hydrogen spectrum fit this equation. The equations themselves were not so important, but the fact that there was a straightforward geometric relationship between experimentally derived lines was. In 1913, the Danish scientist Niels Bohr thought deeply about the pattern of lines in line spectra and considered the new ideas about light conceived by Max Planck, Albert Einstein, and others. He worked with hydrogen and theorized that the hydrogen electron had a fixed energy, that it normally existed in an orbit or stationary state with higher energy orbits available to it. He devised an equation that expressed the energy of each orbit, n, and an equation for the difference in energy between these orbits. This energy gap could then be expressed as a light wavelength. For example, between orbits 3 and 2, the energy corresponds to red light with the exact wavelength of 656 nanometers. Bohr's theoretical equation looked very similar to Rydberg's equation. He may have experienced a rare scientific joy. His theory, worked out largely in his head, produced an equation that matched Rydberg's experimental results. This is what Bohr's mental model of a carbon atom might have looked like. Each electron travelling round the nucleus in a fixed circular orbit with its own energy independent of the others. In fact, this independence was one of the model's main downfalls. Niels Bohr hadn't quite solved the mystery. His equation could only predict the line spectrum of hydrogen. The positions of lines from atoms with more than one electron could not be accounted for. Perhaps electrons in real atoms were not orbiting particles. While Bohr's model was showing some faults, a French scientist named Louis de Broglie considered how electrons in real atoms might differ from the orbiting, negatively charged particles used by Bohr. He suggested that an electron, or any object, had wave-like properties as well as particle-like
That's
properties.
supposed to be a standing wave with a little dot.
Here, waves in water are being diffracted. Diffraction patterns are evidence of wave behavior. Light waves are also diffracted and interfere with each other. This is the pattern formed when a coherent or constant wavelength light source is shone through two slits. This result can only be understood in terms of the interference behavior of waves. Looking from above, and the same wave interference in water. If the wave-like properties of electrons in atoms were important, then perhaps the reason Bohr's model didn't work was that electron waves interfered with each other. De Broglie's suggestion came from his combination of two famous equations derived by Einstein and Planck. The maths is quite straightforward.
So that thing that looks like a V is actually frequency, right? Nothing with any mass can go the speed of light. So for light, C's still there, but for particles, we replace C with V.
Result implies that a wavelength can be calculated for any particle with a finite mass. For a large macroscopic mass like a rubber ball, the calculated de Broglie wavelength is 10 to the minus 30 meters. This wave-like character is insignificant compared to the scale of our field of view, which is of the order of whole meters. A rubber ball's particle-like nature is virtually all there is. The Broglie wavelength for an electron, however, is nearly the same as the dimensions of an atom, about 10 to the minus 12 meters. An electron's wave-like properties become prominent in atoms because the space in which it is observed is so small. To an atom, electrons look like waves. Here, a laser beam is being passed through a wire gauze. The coherent light is diffracted by the wire grid and produces a pattern of spots, similar to the pattern of X-rays diffracted by a single crystal. When a beam of X-rays passes through the many small crystals in an aluminium foil, the X-rays are transmitted in a circle and not to a spot. A typical diffraction pattern of concentric rings or a bullseye is observed. If the slits which produce this light pattern were rotated, a bullseye pattern would be produced. With visible light, a spinning diffraction grating produces a bullseye pattern. We expect X-rays and light to be diffracted because we normally think of them as waves. Now, what if we pass a beam of electrons through thin aluminium foil? The emerging electrons also form a bullseye. Experiments like this were first carried out in 1927. They showed that electrons are diffracted, that both light and electrons exhibit both wave and particle properties. In 1926, Erwin Schrödinger used the sine function, a mathematical wave, to develop a description of electrons that included the de Broglie relationship. The maths is quite involved, but the result revealed electrons as having wave-like properties which dictate their energy and geometry. Schrödinger equation was a description of electrons worthy of their true nature. It is a cornerstone of the quantum mechanical model of electron behavior. There are three important consequences of this model. The first is electron energies are quantized because of their wave-like nature. To fit a wave into a circle, let alone a spherical shell, the wave must be a whole number of wavelengths. This confines the energy of electrons in atoms to quanta, or packets. Second consequence is that an electron's exact position and its exact momentum cannot both be determined at the same time. This arises because we use light to measure these quantities at the atomic scale, And so the act of measuring changes what's being measured.
On that we want to bounce off the electron to find it, right? Changes its energy.
The third consequence of the modern model is atomic orbitals, or those regions of space around a nucleus where an electron with a certain energy is most probably located. These regions can be plotted from the Schrödinger equation, or we can think of them like this. Suppose we took many photographs of the electron in a hydrogen atom and superimposed them on top of one another. What gradually builds up is a picture of the electron cloud, or atomic orbital. We can illustrate this using a graph. In a hydrogen atom, the electron is found most often at a certain radius from the nucleus. However, the electron can sometimes be very close to the nucleus, at other times it can be very far from it. Note the difference between an atomic orbital and a Bohr orbit.
Or the electron will be found at least 100% of the time. It'll slowly get back.
These are energy levels determined by solving the Schrödinger equation.
Chase them out horizontally like that. Just vertically is fine. And you can't really see too well, but they do draw little arrows.
The hydrogen atom has one electron.
Populate.
The helium atom has two in the same orbital. The spherical orbital is larger for the helium atom because of electron repulsion. Lithium, with 3 electrons, has 2 in the same orbital as hydrogen and helium. The third is in a new spherical orbital and new energy level. This electron spends most of its time much further from the nucleus than the other 2. Next, 7 atoms from beryllium to neon have 2 electrons in the first energy level, with the rest in orbitals in the second energy level. In the sodium atom, the orbitals in the first 2 energy levels are filled, and its remaining electron is in an orbital in the third level. This level can hold a further 7 electrons.
Notice that they take very careful.
Potassium starts off the 4th level.
They never go.
Remember that all of potassium's 19 electrons can be found near or far from the nucleus, but at any one time, 2 electrons will be closest to the nucleus. 8 will be further away, another 8 will be even further away, and 1 will be on the outside.
What is true is that the S and P's are filled by the time we get to normal gas, but at argon, not the energy level. Very charged, that part of the
This model of electron arrangement is periodic. We can see that hydrogen, lithium, sodium, and potassium all have a lone outer electron. They behave as a group and tend to lose their valence electron to form 1+ cations. The inert gases with unreactive, filled outer shells are also clearly a group.
Which is true, they're filled, their valence shells are filled, it's not the energy. Helium, neon, yes, but not argon or big.
We said at the outset that an understanding of substances and reactions flows from a knowledge of an atom's outer surface, which we can now describe as the outer atomic orbitals containing valence electrons. Hydrogen gas and helium gas are both lighter than air. They can both be used to make a floating balloon or to make bubble rafts which rise in the air. Helium atoms are unreactive. Their only atomic orbital is filled with a stable pair of electrons. So helium gas is monatomic, 1 atom per molecule.
All the noble gases are monatomic.
When hydrogen atoms meet each other, the atomic orbitals coalesce to form a molecular orbital, which shares a stable pair of electrons and bonds the atoms together.
We'll talk more about that in section 6.
Single hydrogen atoms have an unpaired valence electron and are very reactive. So, hydrogen gas at room temperature is diatomic, 2 atoms per molecule. Could you tell whether a floating balloon contained hydrogen or helium?
This will be helium. All the balloon does is plot. So it's hydrogen. That's why I don't lips anymore for hydrogen. So notice that it, just like section 5.3 did, it summarized the three important, it calls it consequences, or aspects of the quantum mechanical view of the atom. Energies of electrons are quantized because of their wave nature. That relates to the idea that the only allowed energy states are those in which we can maintain a standing electron wave. Heisenberg's uncertainty principle, and the existence of atomic orbitals. I promise that'll be a question on the next test. Now, when that test will be, that's a little in question. We get back on, I think, the end of March. The first class back is a Tuesday. Thursday, as far as I know, is a math schedule. So obviously we can't have our test on Thursday. The following would be, because we get an Easter long weekend, then I believe our next class would be Wednesday, I think. Wednesday, I'm pretty sure, is either CLE or advisory. So I will have to pick a full class to have the test. But if there are several shortened blocks between the time we have a review class, which is scheduled for Tuesday upon our return, I'll just keep going in chapter 6, obviously with the understanding that none of that will be on the chapter 5 test. Okay? So over the break, try as many of the 5-4 review questions as you can, but remember, the test isn't just on 5-4, it's on 5. So the first 3 sections were basically the theories building on each other. We began with eventually Thomson discovering the electron, and then his one-putty model being replaced by Rutherford. Rutherford's planetary model being saved by Bohr. Bohr's model being refined upon using the fact that not only does wave have particle nature, courtesy of Planck, but also particles have wave nature, courtesy of de Broglie. And that then led to the Schrodinger's equation. So you see in the video here that the idea that electrons behave like waves is provable. And the diffraction pattern that we get when we pass an electron beam through an aluminum foil, the idea is that the spaces between the aluminum atoms is small enough that it diffracts, it causes the electrons to diffract. And that spinning diffraction gradient gives us that pulse. Only waves do that. Okay. And when that was proven, that laid the groundwork for de Broglie getting the Nobel Prize. Whereas the first video, this professor, I think in New York University, said, in other words, the electron is a point particle. No, it's not. It's not. It's both. And if that's difficult to understand, it's difficult to understand. So particle wave duality is a foundation of mechanics. The other thing I want to do is quickly give you Raj back. The marks obviously have been posted. Most of the labs were done quite well. The amount of work that most groups put into these is admirable, and that's good. A number of students asked about, let's say that we've had effectively 2 left. And that's, I apologize, but the amount of shortened blocks we have and the amount of stuff we have to get through has resulted in that. let's say you got, I don't know what the first lab was out. Let's say it was out of 20 and you got 19 out of 20. The category I have for labs then has only that in it. So in other words, as much of that category is worth, it might be worth 15%. I'm not sure. 19 out of 20 dictates the amount that that category is contributing to your grade. But let's say on the next lab, you get, say, I think this lab's marked out of 25. Let's say you get 20 out of 25, which is a smaller percentage than 19 out of 20. So when the 19 out of 20 and the 20 out of 25 are averaged, it then means that that mark contributed by the lab category is less than it was before, which means your overall grade will go down a little bit, if that makes sense. And a number of students had asked, how did my mark went down? Well, that's why. And that's true for any teacher who categorizes their grades as they're supposed to, although some teachers don't. And in your course outline at the very beginning of the year, and it's also on Google Classroom, it outlines what's worth what, okay? So maybe that explains it if you wonder what happened to your mark when the lab report. On the other hand, if you did really well in the lab report and the second lab, maybe mark was higher than the first lab, then your percentage, as you would expect, would go up. Okay? So these are in no particular order. Daniel and Duckus, Allison and Alexander, Nicole and Annabelle, Randall and Daniel, Brianne and Ariana, Christina and Leah, William and Samantha, Julia and Marley, the other Samantha and Cassandra, Annika and Lydia, Claire and Lauren. So a couple of things about the lab. A number of groups, when they were observing, rather than just, and he didn't lose marks for this, but I'm mentioning it because in grade 12, it is a distinction that needs to be made. When you're making observations, try to limit your observations to exactly that, just observations. So for example, when you put the nail in the copper 2 sulfate solution, the straight observation is after 25 or 30 minutes, a brown coating appeared on the surface of the nail and the intensity of blue color diminished. That's an observation. An interpretation is over time, copper atoms formed on the surface of the nail and the amount of copper 2 ions in the solution went down. You can't see that happen. You can see the blue color diminishing and you can see the brown solid on the nail. But to say what it is in the context of observations, you can't do that. Or when you put the hydrochloric acid on the magnesium, if your observations were the magnesium atoms dissolved as they lost electrons, as they were replaced by the hydrogen ions, and the hydrogen gas was produced, you can't see that either. What you can see is that the magnesium ribbon over time disappeared, the test tube got really hot, and vigorous bubbling as a result of a gas being produced. Those are straight observations. The other thing, though, that some groups did is I said, if you notice an energy change, put it in, but don't invent one that isn't there. So a number of groups decided that the nail in the copper 2 sulfate was exothermic. So when they wrote the balanced equation, they wrote plus energy on the product side. That test tube did not get hot. The reaction isn't fast enough that you can detect that temperature change. And some people put energy, when they wrote the balanced equation, they thought they needed to put energy. But then when I looked at the data table, there was no mention of that. So if I wrote really with a question marks, that could mean two things. Could mean, did you actually observe it? And then I might add, check your data table. Because if you didn't write it in your data table, it means you didn't observe it. But if you did write it in your data table, make sure that it actually happened. That test tube, just as an example, the iron nail and copper sulfate, that test tube did not get hot. That reaction is far too slow for you to determine the energy. Also, some people said that when a gas was produced, calcium, when the hydrochloric acid was put in the sodium carbonate solution, the test tube got really cold. Well, that was because the reagents were stored right next to an open window. So that's what was going on there. Now, I'm only saying it because if it's actually something you observed and it was obvious, yes. But don't feel you need to put it in there because I just said that every reaction is either EXO or endo. Sometimes the amount of energy is not discernible. And the ones that were discernible, obviously, is the first one, which is endothermic, not exothermic. That's a synthesis reaction, but it's endothermic. So as long as you were holding the copper foil in the Bunsen burner, the synthesis reaction was happening. But when you took it out, it didn't keep the stuff going. So that's endo. The decomposition of the copper 2 sulfate pentahydrate, that was definitely endo. And make sure that the water produced is a gas. Okay. The reverse of that, the decomposition or the synthesis was definitely exothermic. Test tube got very hot as the blue color reappeared and the hydrate was regenerated. But the precipitation reaction, you couldn't tell, there was no temperature change that was discernible there. The reaction of the magnesium and the hydrochloric acid, absolutely, very exothermic. But the reaction of the hydrochloric acid and sodium carbonate, no. There was not a noticeable energy change there. Question number, or reaction number 8. And some people, when they were answering the questions, called it reaction number 7, because remember in the lab handout, there was no reaction 8, but it was really reaction 8. That was exothermic. So hydrogen peroxide decomposes slowly on its own, but it's far too slow for you to notice that it's actually exo. But if you catalyze it, the fact that you speed up the reaction, the same amount of energy is released, it's just released over a much shorter period of time, which means you can detect that temperature increase. Okay. Some people decided, and again, you didn't lose marks for this, it just wasn't necessary. You didn't have to rewrite your data tables. So some people did the data tables, fine, my initials was on them, but then they wrote it out or typed it out. You didn't need to do that. If you wanted to add an extra section to your lab where you were a little more detailed in what you thought, that's awesome. And a lot of people, as I said, did a lot of work with the lab report, which is good. The plan is, and again, this is ideally, I want to try to squeeze in an organic chem lab when we get to chapter 8, which is a model building lab. In a perfect world, before there was such thing as advisory and Greek Olympics and health games and walkathon all on the same day, that lab ideally takes 3 classes because you and your partner are working with a model kit, try to find all the ways to build a molecule having a specific formula, and by then you'll be able to build it, draw it, and name it. But that's in a perfect world. I hope to get that squeezed into chapter 8. But if you look at the schedule when we get back in April, it's decimated. The first week back is Easter Mass. You guys go on retreat the 3rd week back or the 2nd week back? Third week, and that's on what, on a Friday? Okay, so that's shortened. Obviously we have the Easter weekend, we have the Mother's Day Mass, we have Victoria Day long weekend, we have walkathon, house games, Greek Olympics. I don't know why we're a Catholic school doing Greek Olympics to pagan gods. I don't understand that anyway, but the admin team think, well, we've always done it, let's keep doing it. Yeah. Anyway, that all takes cost, and that's why we were talking about this in the science office. It's very difficult to try to maintain the same level of academic content coverage now compared to what it used to be. When there were provincial exams, for example, we didn't have nearly the things we have now because we couldn't afford the parent. And God help us if there were provincial exams now, because we would not finish any grade 12 course. So I lament the fact that the academic rigor has diminished a little bit. Those of us that still think it's important try to do the best we can, but again, there's only so many hours in a day. So I will continue to try to do the best I can. And hopefully we have time for that lab, because that's usually what, if we do have time for it, that's usually the lab that students enjoy the most. And when we get to organic chem, you'll see what I mean by that. So any questions about chapter 5? Anything in the video that didn't make sense? Except that you can part for the Australian accent. Okay, well, let's plan on the first day back being, as far as I know, that Tuesday is a full block when we meet. So we can squeeze in at least a full review class. But between that and the test, until we have a full block, I'm probably just gonna move into chapter 6. Which isn't a departure from the stuff, it's just applying quantum mechanics to the periodic tables. We've done a lot of that already. So between now and when we're done, you still got 25 minutes. Play amongst yourselves if you want. I got to go down and talk to Ms. Walker in the LRC. Yep.